Yeah, so the talk today is going to be on rather very classical material. And I think I'm going to mention the Norbert Wiener at least once during my talk. Everything in the talk today you can find in this recently published paper in Acta Crystallography. It's only 7 pages, so I don't know how I got to like 32 slides, but probably there was a lot of unpacking. And we'll skip some of the slides if needed for the sake of time. So the topic of the talk today is to understand the power spectrum of proteins. And you don't need to know much about proteins for the time being, but these are very important biological macromolecules. And the study of the power spectrum of proteins started already in the 20th century. And there are 2 laws that basically characterize the decay of the power spectrum. One is called the Guinier Law in 1937. And this characterized the behavior of the power spectrum at low frequencies. In particular, it predicts the power spectrum decays exponentially. So phi is the special frequency. Phi hat is the Fourier transform of the electrostatic scattering potential of the molecule. And so what you see here is the modulus squared, or which we'll call the power spectrum of the protein, is approximately its value at the 0 frequency times an exponential decaying function. So you have an exponential and here a quadratic form that depends on this 3×3 moment of inertia matrix or tensor. But so for the Guinier law, at high frequencies, the characterization is given by Wilson statistics. So it's only 5 years later. And it basically predicts that the power spectrum at high frequencies is more or less flat. It is constant when psi is large, when the frequency is high. To derive Guinier law, it's really straightforward. It will take me maybe like 2 lines using Taylor expansion in the next slide. But for Wilson statistics, it's a much more challenging to derive, and this will be the topic of the talk today. So before we start proving things, so I would like to show you a plot from a paper by Rosenthal and Henderson. Henderson is one of the 3 Nobel Prize laureates in the field of Cryo-EM from 2017, a Nobel Prize in Chemistry. And in their paper, they showed the log of F, so this is basically the log of the modulus of the Fourier transform as a function of psi squared. So you see this in units of 1/angstrom squared, or 1/1 distance squared. And you see the exponential decay at low frequency. If you look at the red curve, there is a very quick exponential decay. This is the Guinier law. And there is a 10 angstrom. You see like a cutoff frequency that above which the power spectrum is more or less flat. There is a slow decay due to the atomic structure factor of a carbon. But basically, if it was just the Wilson statistic, you would get the thick black line here. So this type of plots are called Guinier plots, and they are very popular in the field of structural biology. And our goal today is really to understand why at high frequencies we get this type of flat behavior of the power spectrum. Now you see that the power spectrum also drops from, there is a big drop. This is the square root of the power spectrum, just the magnitude of the Fourier transform from the number of atoms that make the molecule to the square root of the number of atoms. Okay, so this could be a big drop for molecules with 10 to the 6 or 10 to the 5 atoms. Okay, so before I show you like a theoretical prediction of how they should look like in theory, this is just like a single molecule. And this is what you get from the experiment if you do, say, a Cryo-EM reconstruction. So again, the same paper of Rosenthal and Henderson, they perform the reconstruction of a certain molecule. and they got decay of the power spectrum. This is what you see in the red curve. Then they did Wiener filtering. Okay, so I promise you that I'll mention Wiener at least once. And they got this thin red curve, okay, because the map is very noisy when you do cryo reconstruction. So you do Wiener filtering, and so you get now, you see the decay of the power spectrum is much faster than what is predicted by Wilson statistics. So then there is a very popular step in Cryo-EM called the B-factor sharpening or map polishing, in which you now apply a filter that actually boosts the high frequencies, the mid to high frequencies. So you get a power spectrum that looks more like the Wilson statistics. So basically, this is the filter that actually boosts high frequencies. Okay, so, and that's a very popular step in Cryo-EM that helps us visualize the molecules and then do atomic fitting and so on. And it is completely based on Wilson statistics. So we should better understand where Wilson statistics is coming from. So I promise you that I'll derive Guinier's law in a couple of lines. So it also helps me to set the stage in terms of notation. So let phi of x be the electrostatic potential of the molecule, and the Fourier transform is phi hat of xi. So this is the Fourier transform that we're all familiar with. Okay, so you just integrate phi against the complex exponential, and we're going to assume that the molecule is centered, so that the center of mass is at the origin. So the integral of phi against each of the coordinates is 0, or you can write it in vector notation in this way. And we're going to assume that the molecule has some finite support. Okay, so suppose that the molecule has size r, so it is completely supported inside a ball of radius r. So phi is 0 outside the support radius. And now let's just do a second-order Taylor approximation of the Fourier of the complex exponential. So you just write it as 1 minus the linear term plus the quadratic term, and then we plug it in, okay, in the Fourier transform formula. So the integral of phi is just going to give us phi hat at 0, the 0 frequency. The integral of phi against x is 0 because we assume that the molecule is centered at the origin, the center of mass is at the origin, and then we're going to have the quadratic term, okay, and this is going to give rise to the moment of inertia. So this is valid whenever we're looking at frequencies below 1 over r, okay, whenever I can say, okay, the residual here is small enough in the Taylor expansion. And this is valid because we made the assumption that the molecule has compact support of radius r. And then the exponential fitting is basically, we're saying, okay, Guinier said, okay, the power spectrum should be non-negative, so the exponential function is a good function to characterize it. And so let's look for an exponential function that has exactly the same second-order expansion. And that's how you derive it Guinier's law. Okay, so I promise you a very simple derivation, and here it is. Okay, Wilson statistics is much more challenging to derive. And it starts with what is called a random bag of atoms. So this is a probabilistic model to describe the protein. So we're going to suppose a random protein, okay, so that's our model, consisting of n atoms whose locations x1 to xn are IID. So you have your protein, and inside it are the atoms, and they're just going to be placed in an IID fashion, randomly inside the container that makes the shape of the protein. So for example, each xi could be uniformly distributed inside the container omega. So you can think of omega as a ball, if it was a spherical protein, or a cube. Though other shapes and distribution are of course possible here. Now, and then we write the electrostatic potential of the molecule, or the scattering potential of the molecule. as a superposition of bump functions centered at the atomic locations. So, so in the ideal case where of point masses, and f would be just a delta function, a spike. But we know the structure factor of atoms is approximately a Gaussian or a superposition of 5 Gaussians. But so think of it just as a very narrow function centered at each of the xi's. And there can be different f's for each atomic species, but to make it simple today, let's just assume that all the atoms are identical. In any case, you can just think of them as carbons. Okay, this gives rise to the most contribution to the power spectrum, if you look at proteins. So that's our model for the electrostatic scattering potential of the molecule. And then if we take its Fourier transform, it's very simple, right? We know that the Fourier transform when we shift the function is just the Fourier transform of the function times the phase modulation factor. Okay, and then I can take the f at psi outside, and what is left is a sum of complex exponential functions. So basically, what we'd like to understand today is how a sum of Fourier exponentials behave when these xi's are random. Looks like a very simple task. Okay, so that was, now let me give you Wilson's original argument, okay, for why the power spectrum at high frequency should look flat. So that was also Wilson's starting point. And then he said, by the way, his paper in Nature from 42 is even less than a page, okay? So, so very easy to read if you want to read his paper. Okay, so he took the modulus squared, so fh squared we can pull outside, and we have the squared of the sum of exponentials. And now that we square it, we just multiply by the complex conjugate. So now we get a sum over n squared terms, okay? Now a double sum over I and j. And because it took complex conjugate, it's xi minus xj. And then he said, okay, let's separate the sum of n terms to the terms on the diagonal where I equals to j. And all of them contribute 1 when I equals to j. So here you have 0. So that's how we get the n. And then we have the off-diagonal terms when I is different than j. We get an order of n squared such terms, okay? But they all oscillate widely, especially at high frequency, okay? When psi is large, they oscillate more and more and more frequently. So he said, oh, well, so this must be negligible compared to n. And that's how we get n fh squared. And for an ideal point mass, if it's a delta function, then its Fourier transform is 1. So, well, we just get n. And that's Wilson statistics. So that's how Wilson obtained his law, okay? As you can see, it was a bit of a hand-wavy argument that I would like to make today more rigorous. Especially, we'd like to understand how can we get such a beautiful cancellation here, okay? That the sum of n squared terms would be smaller than n. So in particular, even if you think of this term as being just random IID, random variables, then the size of each term is 1, okay? So the expectation, if the expectation is 0 and the sum and the size is 1, the variance is 1, then we expect the size of this guy to be of the order of square root of the number of terms, like a random walk. So this will be square root of n squared. This should be comparable to n. It should be also of order n. So it's unclear how we actually get the cancellation. And also we need to understand the role that psi plays, because if I set psi to 0 here, okay, then all these terms here become 1, and then like they should, the power spectrum should be like n squared, okay? And as psi grows, then suddenly this becomes negligible and we get to n. So somehow this psi plays a very important role, and we need to understand, okay, in this argument that I gave before, what makes the oscillation to magically cancel each other? Okay, so let's start. Okay, as applied mathematicians, we look at this problem, and I already said, okay, maybe random walk, so we think of central limit theorem. We have a sum of n terms, so it makes sense to try perhaps the central limit theorem. We have n IID random variables here, okay, because the xi's are random, are IID, and xi is just a parameter of fix. So for a fixed xi, you think of it as a sum of n IID random variables. So okay, let's do the central limit theorem, and we can finish the talk now, because then for every xi, this will be normally distributed. Everyone can be happy, and the end of the talk. But we need to apply stuff more cautious, okay, to be a bit more careful here. Because if the container omega is fixed in the limit when n goes to infinity, this means that I'm adding more and more and more and more atoms into my container. And this means that the density of the atoms grows indefinitely. So I'm no longer in the physical regime, because clearly the density of atoms in a protein is bounded, okay? And if you look at proteins, they have more or less of fixed density. So I cannot just take the limit here and goes to infinity. So I need to do a little bit of scaling here. So if I want to keep the density of atoms fixed, then I should also allow the container omega to grow with n. So as I'm placing more and more and more atoms inside, I'm going to let my container grow with the number of atoms in order to let the density inside to be fixed. So the way we're going to be more careful is to decorate omega with subscript n, to remind us that omega n should be, that the volume of omega n should be proportional to n, or if you wish, the length scale is proportional to n to the 1/3, because we're in 3 dimensions. Or I can write that omega n is just n to the 1/3 omega 1. Okay, like a unit cell, if you wish, if I would just replace a single atom. So now I can write the xi's as n to the 1/3 yi, okay? So for example, if the atoms were uniformly distributed inside the omega 1, then I would say that yi's are just uniform in omega 1 and IID. If you don't want uniform, then I just IID in general. So now we replace the xi's with n to the 1/3 yi. And now you see that I can no longer apply the central limit theorem. Okay, why? Because now the random variables, they explicitly depend on n. So I cannot just take the limit n goes to infinity here when the random variables themselves depend on n. So, but we can still compute moments. So that's what I'm going to do next. So let's do the first order moment, just to take the expectation. Let's see what's the expectation of the Fourier transform. So I still have n terms, and I can use the linearity of expectation. So, and there are IID, so I just need to take the expectation of a single term. So we get n times the structure factor times expectation of the complex exponential. And the expectation of the complex exponential, I just write it as an integral now against the density of the probability density of where to find the atom inside omega 1. Okay, so it's just the Fourier transform of G, of the density. So you see the expectation of the Fourier transform is n times Fa times G hat at n to the 1/3 xi. And already you see that if n is a large parameter in the problem, the number of atoms, and we want to understand the behavior of at large xi, then we need to understand something about the decay of G hat at large xi, because xi is multiplied by a large parameter here. So the decay rate of G hat of the Fourier transform is going to play a very important role in the analysis. And clearly different container shapes and different choices of G can lead to different behavior of the Fourier transform. So before stating non-theoretical results, I would like to now give you a couple of examples so we see what to expect from the Fourier transform of G. So the first example that I'm going to show you is a uniform distribution in a ball. So here omega-1 is just a ball of radius 1, denoted B. So here is the uniform densities in a ball. So that's the volume of the ball. That's the characteristic function of the ball. And it's a radial function. So that's a property that you can easily use to then compute calculate the Fourier transform in closed form. So here is the closed form Fourier transform of the density inside the unit ball. And you can see that there are two terms. If I care about the behavior at high frequencies, then I see that it decays like 1/xi². Okay, so the decay is 1/xi². The next example that I'm going to do is the cube. Okay, the unit cube of unit volume, and now the density is a product of 3 rectangular window functions. Okay, between -half. The Fourier transform of a window function, we know it to be the sinc, sin of xi/xi. And now we see slightly different behavior. So if I go, for example, along in a direction that is perpendicular to one of the faces of the cube, for example, if I go in the direction of the x-axis, then 2 of the sinc functions are just 1, and the third will give me a sinc function, sin of xi/xi. So you see that now the decay is slower, it's just 1/xi if I go in the direction. But if I go in the direction that is not perpendicular to one of the faces, then I can get a faster decay rate. So for example, if I go in this direction, then each of the sinc functions is now active, and I'll get a decay that is like 1/xi cubed. So I think that now we're ready to state, after we saw those two examples, we're to state existing theoretical result about the decay rate of the Fourier transform for containers of general shape. Okay, so here is a very classical result. You can find in textbooks. So I took it from the book of Stein and Shakarchi on functional analysis. And here is a theorem. So suppose omega in RD, so now D can be even not necessarily 3, as we care about, is a bounded region whose boundary M has non-vanishing Gauss curvature at each point. Then if we look at the Fourier transform of the characteristic function of omega, then it decays as xi to the minus d plus 1/2. Okay, so for example, if we take the ball, okay, in 3 dimensions, so d equals to 3, and we know that the ball is non-vanishing Gauss curvature, okay, it is a constant Gauss curvature, then you see that it's exactly the 1/xi², as we saw in the example. The second part, if M has M non-vanishing principal curvature at each point, then the decay is like 1/xi to the m plus 2/2. So the example of the ball, okay, we have 2 non-vanishing principal curvatures, and then you get 1/xi². In the case of the cube, you have 0 non-vanishing principal curvature. Okay, you have a flat side. So then you get 1/xi. Okay, that's the decay that we saw before. A more recent result, I'm going to state now from a paper by Brandolini, Hoffman, and Yosevich. And this is about the decay rate, or the L2, the average L2, the spherically averaged power spectrum. Okay, so now instead of just looking at different directions, we're going to look at the spherically averaged power spectrum. We're going to average over all possible directions. And even though that we saw that the decay rate in different directions could be different, okay, as the example of the cube illustrated, okay, when we got different decay in different directions, it turns out that for a large family of containers, so this includes convex sets and open sets with sufficiently smooth boundary surface, so sufficiently smooth, for example, C to the 3/2. The theorem of Brandolini, Hoffman, and Yosevich says that the decay rate, the spherically average decay rate of the power spectrum is exactly the same as that of the ball. Okay, so the ball was actually not just an example, but it's actually illustrates what happens in much more generality. So here is the theorem. So suppose omega in RD is a convex body or an open bounded set whose boundary is C to the 3/2, then the integral over the unit sphere in D dimensions of the power spectrum, basically the Fourier transform, the magnitude of the Fourier transform squared of the characteristic function of the set, decays as 1 over k to the d plus 1. Okay, so here we didn't take, so k is the radial frequency. If we were to take the square root, then we'll get the 1 over k to the d plus 1 over 2. And for d equals 3, you'll get the 1 over k squared behavior. So now we're in position to state and prove the main result that fully characterizes the regime of validity of Wilson statistics. Okay, so the first part, okay, so if we consider the random bag of atoms model, then the expected power spectrum as, so here is the power spectrum expectation, it has two terms. One is n, okay, that's the constant that to which we converge at high frequencies, plus n minus 1, the squared Fourier transform of G8 at n to the 1/3 side. The second part, okay, if the container satisfies the same conditions in the paper of Brandolini et al., okay, if it's a convex body or an open set with C to the 3/2 boundary surface, and we place the atomic positions uniformly at random, then the expected spherically average power spectrum satisfies the following, okay? So here is the expected spherically average power spectrum, and it has two terms. The first is the constant, the flatness of Wilson statistics, plus little o of n, and this happens for frequencies, for radial frequencies k, above n to the minus 1 over 12. So that's the cutoff frequency above which Wilson statistics holds. Okay, so that's, and the third part, if you look at more exciting proteins, maybe they have a surface that is more fractalish or something that decays different than the ball of 1 over psi squared, then you can also derive a cutoff frequency for that. Okay, so I'm now going to prove for you the first two parts. The third part is very easy to prove as well. So the first part, we're just going to start the same as Wilson. Okay, so we're going to square the Fourier transform and separate into the diagonal and off-diagonal terms. And now we're going to take the expectation. So here, this term is not going to change throughout. This term is not going to change throughout. So only the double sum here, I'm going to play with it, okay? So I'm going to take the expectation of this. Because we're looking at the off-diagonal terms, where I is different than j, then yi and yj are independent. So the expectation of a product of independent random variables is just the product of the expectations. Okay, so that's what I have here. And they're also identical. So now it's just the modulus squared of one of them. Okay, because here I have a complex conjugate. And this modulo squared expectation inside is what we call before G hat. It's just the Fourier transform of the density. Okay, so very easy. Okay, you almost didn't feel it. Okay, we derived the first part. The second part is almost just as easy. Okay, given the results of Brandolini. So we already proved this in the first part, and now assuming that f and also f hat are radial functions, okay, like the Gaussian or the delta function, then the expectation of spherical average power spectrum satisfy the following. Okay, so I'm now going to take the integral over the unit sphere in 3 dimensions and average. So the average of the constant is the constant. I just need to average this function that has some variation over the unit sphere. But we know that in 3 dimensions, okay, the result of Brandolini tells that this is going to decay as 1 over k to the 4. Okay, but I also need to now take the power 4 of the n to the 1/3. So, but this is going to be multiplied by n squared. Okay, so n squared minus, so n to the 2 minus n to the 4/3 is going to give me n to the 2/3. Okay, so this term behaves like n to the 2/3 times k to the -4. And now you ask yourself, okay, when is it going to be negligible compared to n? So it's going to be negligible compared to n whenever k is larger than n to the -1/12. So when n is larger than, when k is larger than n to the -1/12, then this term is negligible compared to n, and that's the regime of validity of Wilson statistics. That's the cutoff frequency, n to the -1/12. So that was not hard to prove. So now, if we look at proteins, the protein density is about 0.8 Dalton to angstrom squared, to angstrom cubed. And so now if you put the numbers and say, for example, for the example of the ball, then you get the cutoff frequency is this constant 0.28 times the radius to the -1/4, or 0.31 the molecular weight to the -1/12. Okay, so remember that the number of atoms is proportional to the molecular weight, and here is the dependency on the power of -1/12. Here you get -1/4 because the volume is related to the radius, okay, in 3 dimensions as our cube. So you can plot this cutoff frequency as a function of the radius in angstroms, and you see that the cutoff frequency increases obviously with the size of the protein. For a protein of about 80 angstrom, you get like 10 angstrom as the cutoff frequency, or 60, it will give about 10 angstrom. But you see that it's a rather robust, because this dependency is like -1/12, or even with the radius is -1/4. It's a very robust quantity. So even if you go to very, very small proteins, the cutoff will be, say, 8 angstrom. If you go to very, very large proteins, it will be like 12 angstroms. Okay, so it changes from 8 to 12, not by this is not a dramatic difference, and that's why they observe that around 10 angstrom, it's where the cutoff frequency. So here I plotted for you just 2 cases of, in the case of a ball, the theoretical predictions of that you'll get with a molecule size 100 angstrom. Okay, that's the blue oscillation that you see here, and for a molecule size 25 angstrom, that's in red. So you see that for the larger one, we see maybe around here at 0.01. So this will correspond to like 10 angstrom. For the smaller one, perhaps here it becomes flat. So again, this is a complete agreement with what we see, the empirical evidence about the validity regime of Wilson statistics. Now we also see that the transition to Wilson statistics, it behaves like 1/k to the 4. Okay, so if you ask us, okay, so how quickly do we reach the Wilson statistics? So what's the decay look like? It looks like 1/k to the 4, the decay to this constant value of n. And at first, like, you may think that this 1/12 exponent is somewhat mysterious. Okay, where this 1/12 comes from, but it really comes from a product, okay, of the dimension 3 that led us to this scaling of n to the 1/3 for the, we want to keep the density constant, and the decay rate of the Fourier transform, the 1/k to the 4. So this 4 and 3 together, this is what gave the cutoff frequencies of n to the -1/12. You can also ask yourself, okay, so Amit, you only computed the expectation, but maybe in practice the fluctuation of the power spectrum will overwhelm the mean. So we also need to check that the variance is smaller than the mean. And okay, I checked. Okay, we check it, and I don't want to go into the details. And it's indeed the fluctuations. Whenever you are above the cutoff frequency, the variance is, if you take the square root, the standard deviation is going to be little o of n. So it is indeed smaller than the flat value. Okay, so now I want to discuss applications in Cryo-EM. So I already mentioned the existing application of map sharpening, and this is done routinely whenever you do a reconstruction. After you do the Wiener filtering, then you do this B-factor correction or B-factor flattening, and it's all based on Wilson statistics. And this allows to do to fit an atomic map to better model the protein. I'm not going to tell you how, but it's also used to reason about and extrapolate the number of particle images required to high resolution reconstruction. So for example, let's say you did an experiment, cryo-EM experiment, and you reconstructed the molecule, let's say, to 6 angstrom resolution using a certain number of images, and now you ask, okay, how many images do you need to get to 3 angstrom? Then Wilson statistics allow you to answer that question. Now I'd like to discuss a few generalizations of Wilson statistics. So these are statistics that do not appear in Wilson original paper or even in later work. That I started to think about other parts in the computational pipeline of Cryo-EM, and you see that Wilson statistics or generalizations of Wilson statistics can be quite helpful there as well. So one potential application is 3D refinement. So that's, you don't need to know a lot about Cryo-EM, only to know that that's the part where actually the 3D reconstruction is being done, like taking very noisy Cryo-EM images and as input and giving as output a 3D reconstruction. And perhaps one of the most popular software, reconstruction software nowadays is called Relion, from Sherris and his group at Cambridge. And it's basically a Bayesian inference framework that makes some power assumption about phi hat, okay? And basically it treats phi hat, all the frequencies, as having a Gaussian distribution with 0 mean and some variance, okay? And assuming no correlation between different frequencies, so the covariance structure of the covariance matrix of this phi hat is just diagonal. So that's what is the assumption in Relion. And they make some even further simplification like that, the variance is just a function of the radial frequency. Okay, so it's really a radial function. But now, so let's see if that's really supported by Wilson statistics. Okay, so we can do the same yoga that we did to derive Wilson statistics to say also derive the covariance of phi hat at psi1, psi2. Okay, so this would just be the expectation of phi at psi1 times phi at psi2 after complex conjugate minus the product of the mean. Okay, the mean we already computed in the beginning of the talk. Okay, remember that was g hat. Okay, so that's the product of the means, and you can do exactly the same yoga to compute the expectation of this product. Okay, so this is what you get. Okay, so now you get two terms. And then when you subtract to get the covariance, you see that these two terms almost completely, they're almost completely the same and cancel each other. So we just get minus n that I take outside, and this is the covariance. Okay, so if you think of it as a covariance matrix, you see that it has two terms. One is what looks like a Teplitz matrix that depends on psi1 minus psi2, and one is a rank 1 matrix that depends on psi1 times a vector that depends on psi2. But really, okay, so already at this point, if in general covariance matrix for a volume or a 3D map of size L cubed voxels, it can be huge, right? It will be of size L cubed by L cubed. You need like order of L to the 6 parameters or entries. But we see that it really depends only on this function g hat. So it's only going to depend on L cubed parameters, not L to the 6. And furthermore, if you're going to make the same assumption of Reliant, that Reliant does, that it's only a function of the radius, then it's just like in Reliant, it's only going to depend on L parameters. And now you can also ask yourself, okay, does the assumption of Reliant make sense that it's a diagonal matrix? Well, for frequencies that are above n to the minus 1/3, which is a relatively very low frequency, we can neglect this part, the rank 1 matrix, corresponding to this guy, okay, because we have here a product of two decaying functions, okay? So this is going to be much smaller than this one. And this guy is simply a banded matrix, okay? It's largest when psi1 equals psi2, so it's largest on the diagonal, and it decays as you go off the diagonal, okay? So it's really a banded matrix with number of bands that proportional to n to the minus 1/3. So indeed, that supports the approximation made by Reliant, but it also tells you how you would go about correcting and making the approximation of Reliant more accurate, especially if you want to go to low frequencies and also keeping a few more of the diagonals for a better approximation. And especially you don't want to neglect the mean, okay? So better not approximate the mean as 0 as done in Reliant, because at low frequency, it's actually the mean that dominates the variance. For example, at 0 frequencies, there is no variance at all, okay, because we know that there is a constant number of atoms, okay, so. Okay, so now I want to mention one more generalization, and this was motivated by recent work that we're doing in my group for when we try to develop method of moments approaches for 3D reconstruction in Cryo-EM. And this story all began with Tzvi Kam from the Weizmann Institute, that in the late 70s, early 80s, he proposed an autocorrelation method for determining the 3D structure from the moment statistics of the 2D noisy images in Cryo-EM. And also this applies to other imaging modalities, like people now that do X-ray free electron lasers and others, but the idea that CAM was able to relate basically the covariance matrix of the 2D images with the 3D structure of the molecule. So his original method is limited only to uniform distribution of viewing directions. So in recent work, we try to extend it to non-uniform distribution of viewing directions. And also to reconstruction directly from a micrograph without any particle picking. So I know that many of you in the audience are not familiar with Cryo-EM, so don't worry about the buzzwords that I mentioned now. This is just to serve as a motivation to what I'm going to show you next. Okay, so the methods we developed is they work at low resolution. We get low resolution reconstruction with them, but we have really hard time to put them to high resolution, and perhaps what I'm going to show you next may serve as a possible explanation for the difficulty that we observe with in practice. So already you see something about the power spectrum that may hint about a difficulty. Okay, that we see the power spectrum at low frequency starts at n squared, and at high frequency, with some statistic, it goes to order n. So it drops from order of n squared to n. Okay, so now if we're going to use the information in the power spectrum, so we're going to do least squares or any kind of fit, it's going to give much more emphasis to low frequencies than to high frequencies. Okay, so that's one issue. The other issue is that regardless of what I showed you, regardless of the atomic positions, the power spectrum at high frequencies is always flat. It's always the same. So it's not going to help us to distinguish between different 3D structures. So as long as they have roughly the same shape, the same G hat, then we're not going to be able to differentiate between different random realizations of where you put the atoms inside the container. So there is this kind of universality of the power spectrum that obviously I'm looking here at the expectation. Okay, so I'm ignoring the variance and so, but you already see like the origins of the ill conditioning of the program. So what about higher order spectra, which is what you'd get when you use the higher order moments? So so the other generalization of Wilson statistics that we did is to find expectation of higher order spectra beyond the power spectrum. So you can look, for example, at the expected bispectrum in the random bag of atoms model. So now look at the expectation of a triple product of Fourier coefficients. Okay, and you can play the same game. Okay, now you get a triple sum. Okay, and you do all of this. I don't want to go into the details. Again, there is some very nice structure that follows. And if you want to get features that are shift invariant, just like the power spectrum that is invariant to shift, so the bispectrum is invariant, but this means that it's not every 3 frequencies that I plug inside, only those that satisfy the Xi1 plus Xi2 plus Xi3 0. Okay, so that's the slice of the bispectrum of the third order moment tensor. And that's what we get for the expected bispectrum. And again, you see this drop, okay, that the bispectrum can now go from n cubed to n at very high frequencies. So I'm not doing for you all the Wilson's derivation in this case, but you can just take my word for it, okay, that it will go from n cubed to n. And now the ill conditioning is even more pronounced, okay? That if you have a molecule, say, with 10 to the 4 atoms, then the bispectrum ranges like 8 orders of magnitude. Okay, it will change from n to n cubed, so a factor of 10 to the 8 difference. Okay, so I want to conclude by just a quick discussion, then to summarize. So Wilson statistic is an instance of universality phenomena. All proteins, regardless of their shape and specific atomic positions, exhibit a similar power spectrum at high frequencies. And this universality is a blessing and a curse at the same time. On the one hand, it enables to correct the magnitudes of the Fourier coefficients of the reconstructed map so they agree with the theoretical prediction. So this is what we saw in the B sharpening and the polishing at the very end of the reconstruction process. On the other hand, it implies that the high frequency part of the power spectrum is not particularly useful for structural determination, as it does not discriminate between molecules. The generalization of Wilson statistic to higher order spectra shows that the bispectrum is ill-conditioned and becomes flat at high frequencies. This observation may help explain difficulties of the autocorrelation approach as a high-resolution reconstruction method. And one caveat in all this story about Wilson statistic is that it ignores correlation between atomic positions in the protein. Okay, so for example, it is well known that the power spectrum deviates from Wilson statistics at frequencies that correspond to interatomic distances associated with secondary structures, such as alpha helices, which produce a peak at 10 angstrom, and beta sheets, which produce a peak at 4.5 angstrom. Okay, so to summarize, we presented the first formal mathematical derivation of Wilson statistics. The cutoff frequency, n to the minus 112, is the frequency above which the power spectrum is approximately flat. The random bag of atoms model enables derivation of useful statistics beyond the power spectrum, such as the 3D covariance and higher order spectra like the bispectrum. And this generalization of Wilson statistics can potentially be applied to other aspects of the computational pipeline of single particle analysis in Cryo-EM beyond B-factor correction. So I would like to thank all of you for listening, and to thank the funding agencies and foundation for their support.